A black hole has no hair. That's not a joke. It's a theorem, the no-hair theorem, and it's one of the most profound statements in all of physics. What it means is this: a black hole is completely described by just three numbers: its mass, its electric charge, its angular momentum, how fast it's spinning. That's it. Three numbers. Everything else, every detail about what fell in, every bit of structure, every complexity is gone, erased, irrelevant. A black hole made from a collapsed star is identical to a black hole made from compressed hydrogen. Gas is identical to a black hole made from a million textbooks, is identical to a black hole made from pure energy, as long as they have the same mass, charge, and spin. Black holes are the simplest macroscopic objects in the universe, simpler than atoms, simpler than elementary particles, simpler than anything else that can hold mass and exist in space. I'm Leonard Susskind, and I'm going to explain why black holes are so simple, why the no-hair theorem is true, why all that complexity, all the information about what fell in gets hidden behind the event horizon in a way that makes the black hole's exterior geometry completely generic, and why this simplicity is both beautiful and deeply troubling. Let me show you why. Start with what a black hole actually is. In general relativity, a black hole is a region of space-time where gravity is so strong that nothing, not matter, not light, not information, can escape from inside a boundary called the event horizon. The event horizon is not a physical surface. It's a point of no return in space-time. Cross it going in, and all your future paths point toward the center. There's no trajectory that leads back out. Not because you lack fuel, because the geometry of space-time itself is structured such that out is in your past, not your future. You'd have to travel backward in time to escape, and that's impossible. What determines where the event horizon is? Just the mass of the black hole? For a non-rotating, uncharged black hole, the simplest case, the event horizon is at a radius called the Schwarzschild radius, given by r equals 2gm divided by c squared, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. For a solar mass black hole, the Schwarzschild radius is about 3 kilometers. For a black hole with 1 million solar masses, it's about 3 million kilometers, roughly the size of the sun. But here's what's remarkable. That's all you need to know. The mass determines the radius determines the event horizon, and the event horizon determines the geometry of space-time outside the black hole. The entire exterior space-time geometry is fixed by the mass alone. This is the Schwarzschild solution to Einstein's equations. It's a vacuum solution, no fields, just empty, curved space-time outside the horizon. And it's unique. Every non-rotating, uncharged black hole has exactly the same exterior geometry up to scaling by mass. Now add rotation. A rotating black hole is described by the Kerr solution, discovered in 1963. It has two parameters, mass and angular momentum. The geometry is more complicated. The horizon is oblate, flattened at the poles. There's an ergo region outside the horizon where space-time itself is dragged around the black hole. But the solution is still unique. Every rotating black hole with the same mass and spin has exactly the same exterior geometry. Add electric charge. A charged black hole is described by the Reisner-Nordstrom solution, or if it's also rotating, the Kerr-Newman solution. Now you have three parameters: mass, charge, and angular momentum. And again, the solution is unique. Every black hole with those three numbers has identical exterior geometry. But here's something fascinating about charged black holes. In principle, they can have two horizons, an outer event horizon and an inner Cauchy horizon. Between them is a region where bizarre things happen. Quantum field theory predicts the Cauchy horizon is unstable, probably destroying anything that tries to cross it. We don't fully understand this region. It's where general relativity's predictions break down and quantum gravity must take over. In practice, astrophysical black holes probably have negligible charge. Matter falling in is electrically neutral on average, and any significant charge would be quickly neutralized by attracting opposite charges. So real black holes are described by the Kerr solution, mass, and spin only. This is the no-hair theorem. Black holes have no other properties, no bumps, no irregularities, no structure, no memory of what they formed from. 3 numbers completely specify the exterior geometry. Contrast this with literally any other object. A star has mass and spin, but it also has temperature, chemical composition, density profile, magnetic fields, surface features. A planet has mass and spin and charge, but also topology, geology, atmosphere, internal structure. Even an atom has energy levels, quantum states, orbital structure. A black hole has none of this. It's perfectly smooth, perfectly simple, perfectly generic. Why? Because all the complexity is hidden behind the event horizon. Everything that falls in all the structure, all the information, crosses the horizon and is lost to the exterior. The outside world can't see it, can't probe it, can't distinguish one black hole from another except by measuring mass, charge, and spin. This leads to a profound consequence. Black holes have enormous entropy. Entropy measures the number of microstates, the number of different microscopic configurations that correspond to the same macroscopic state. For a black hole, that number is staggering. The entropy of a black hole is proportional to the area of its event horizon. S equals A divided by 4, where A is the area in Planck units. For a solar mass black hole, the entropy is about 1077. That's more than the entropy of every atom in the sun by a factor of billions. What this means is there are 1077 different ways to build a black hole with that mass. Different configurations of matter and energy, different arrangements of particles, different quantum states, all producing the exact same exterior geometry, all indistinguishable from the outside, all encoded somehow on the horizon in a way we don't fully understand. This connects directly to the information paradox. When you throw something into a black hole, all the information about what you threw in is hidden. The black hole doesn't change except by gaining a tiny bit of mass. An outside observer can't tell what fell in, can't reconstruct it, can't distinguish it from any other thing with the same mass. The information is behind the horizon, and if the black hole eventually evaporates via Hawking radiation, the question becomes, does that information come back out in the radiation, or is it lost forever? This was the central debate between Stephen Hawking and me. Hawking said the information was lost. I said it must come out. We now believe, though we don't fully understand, how that the information is preserved, encoded in subtle correlations in the Hawking radiation, but the mechanism is still mysterious. Now let me tell you why black holes are so simple from the perspective of general relativity. Einstein's equations relate the curvature of spacetime to the distribution of matter and energy. Outside a black hole, there's no matter, no energy, just empty spacetime. So the equations reduce to vacuum equations, the Ricci tensor vanishes. These vacuum equations have very few solutions. In fact, the Birkhoff theorem says any spherically symmetric vacuum solution must be the Schwarzschild solution. There's no other possibility. Uniqueness is built into the mathematics. Similarly, the Kerr uniqueness theorem says any stationary, asymptotically flat vacuum solution with an event horizon must be the Kerr solution. Rotating black holes are unique. This is extraordinary. General relativity, with all its complexity, all its nonlinearity, all its 10 independent field equations, reduces to a handful of simple solutions for black holes. And those solutions are completely determined by a few conserved quantities. Why are those quantities conserved? Because they're associated with symmetries. Mass is conserved because the laws of physics don't change with time-time translation symmetry. Angular momentum is conserved because the laws don't change with rotational symmetry. Charge is conserved because of gauge symmetry and electromagnetism. These are deep, fundamental symmetries. And black holes, being pure solutions of the field, equations with no additional structure, respect those symmetries perfectly. They can't have any other properties because there are no other conserved quantities to label them with. This is why black holes are simple. They're the purest expression of space-time geometry with no additional matter or structure to complicate things. Now let me address something that troubles people. If black holes are so simple, why are they so complicated to study? Why do we not fully understand them? The answer is the interior. The exterior is simple. 3 numbers. Done. But the interior is a different story. Cross the event horizon, and you're inside. The singularity, a point of infinite curvature where the laws of physics break down, is in your future. You can't avoid it. You'll hit it in finite time, and when you do, general relativity predicts that tidal forces become infinite. You're stretched to infinite length and crushed to 0 width. You cease to exist. But we don't believe this is really what happens. We think general relativity breaks down near the singularity. Quantum gravity, whatever theory unifies quantum mechanics with general relativity, must take over, and we don't have that theory yet. So the interior is complicated not because black holes are complicated, but because we don't understand the physics where space-time curvature becomes so extreme that quantum effects dominate. The exterior is classical, general relativity works perfectly, and the exterior is simple. Now, let me tell you about astrophysical black holes. Real black holes formed from collapsing stars. When a massive star runs out of fuel, it collapses. If the core is heavy enough, more than about 3 solar masses, nothing can stop the collapse. Not electron degeneracy, pressure. Not neutron degeneracy, pressure. Gravity overwhelms all resistance. The core collapses to a black hole. During the collapse, the star has structure, density, gradients, composition, rotation, magnetic fields, complexity. But once the event horizon forms, all that complexity is hidden. The exterior geometry settles down to a Kerr solution rotating black hole described by mass and spin. The collapse erases all the details. The black hole forgets what star it came from. This settling down process is called ring down. The newly formed black hole wobbles. It emits gravitational waves. But the oscillations decay rapidly. Within milliseconds, the horizon becomes smooth. The geometry becomes stationary. The black hole becomes simple. We've observed this. In 2015, LIGO detected gravitational waves from 2 black holes colliding. The signal showed 3 phases. In spiral, the 2 black holes orbiting each other, gradually getting closer, merger, the 2 horizons touching and combining, and ring down, the final black hole settling into a Kerr solution. The ring down signal matched the predictions of general relativity perfectly. The oscillation frequencies depended only on the final black hole's mass and spin, nothing else. The merged black hole was simple. This is observational confirmation of the no-hair theorem. Real black holes, formed from violent astrophysical processes, are described by Kerr solutions with just 2 numbers. Now let me tell you about the causal structure of black holes, because this is where their simplicity becomes geometrically profound. Physicists use Penrose diagrams to visualize the causal structure of space-time. These are conformal diagrams where every point represents a sphere in space-time, and light rays travel at 4-5 degree angles. For a black hole, the diagram is remarkably simple. The event horizon is a diagonal line. Everything inside it flows inevitably toward the singularity at the top. Everything outside can escape to infinity. The diagram is perfectly symmetric, perfectly clean. No irregularities, no complications, just pure causal structure determined entirely by the mass. Compare this to the causal structure of literally anything else. A star has a complex interior with different density regions, convection zones, fusion shells. The causal structure is messy and depends on detailed physics. A planet has geological layers, phase transitions, compositional variations. The causal structure is complicated. A black hole's causal structure is a few clean lines on a diagram. That's it. That's all there is. The simplicity is geometric, built into the very fabric of space-time. This geometric simplicity has profound consequences for quantum gravity. String theory, loop quantum gravity, every approach to unifying quantum mechanics with general relativity has to explain black hole thermodynamics. And that explanation becomes tractable precisely because black holes are so simple, there are fewer degrees of freedom to account for. The problem is more constrained. In string theory, we can count the microstates of certain extremal black holes and reproduce the Bekenstein-Hawking entropy exactly. This is one of string theory's greatest successes, and it works because extremal black holes are maximally simple. They have enhanced symmetries that make the calculation possible. Now let me tell you about extremal black holes. These are black holes where the charge or spin is at the maximum value allowed by general relativity. For a rotating black hole, there's a limit to how fast it can spin. If it spins too fast, the event horizon disappears and you get a naked singularity, a singularity visible from the outside, not hidden behind a horizon. Cosmic censorship, the idea that singularities are always hidden, says this shouldn't happen in nature. An extremal black hole is spinning exactly at this limit. The horizon is still there, but just barely. The geometry is highly symmetric, and the entropy is zero. This is bizarre. An extremal black hole has no entropy, no microstates, no information capacity. It's maximally simple even by black hole standards. We don't think extremal black holes exist in nature. Any realistic black hole will have some charge or spin below the extremal limit. But the mathematical solutions are well defined, and they're interesting theoretically because they have enhanced symmetries that make them easier to study in quantum gravity. Now let me connect this to thermodynamics, because black hole simplicity is deeply connected to black hole thermodynamics. Black holes have temperature. The Hawking temperature is inversely proportional to mass. T equals Tc cubed divided by 8 pi gmk, where A is Planck's constant and K is Boltzmann's constant. For a solar mass black hole, this is about 60 nanokelvin, incredibly cold. Black holes have entropy proportional to area. S equals Kc cubed A divided by 4 of G. For a solar mass black hole, this is about 1077. And black holes obey the laws of thermodynamics. The first law relates changes in mass, area, and angular momentum. The second law says black hole entropy never decreases. The third law says you can't reach zero temperature or extremality in finite time. Black holes are thermodynamic objects. And thermodynamics is about coarse graining, about ignoring microscopic details and focusing on macroscopic properties like temperature and entropy. Black holes are simple because we're only seeing their thermodynamic properties. The microscopic details are all hidden behind the horizon, encoded in the entropy. From the outside, we see only the coarse-grained macroscopic state. This is why black holes are simple. They're thermodynamic systems in the limit where all microscopic information is inaccessible. Only the macroscopic conserved quantities, mass, charge, spin, are visible. Let me end with a philosophical point. Black holes teach us something profound about information and complexity. You might think complex objects are fundamental. That complexity is the natural state. That simplicity is rare and requires special conditions. Black holes show the opposite. Simplicity is the generic state, complexity is the exception. When gravity is strong enough, when matter collapses sufficiently, all complexity is hidden. All structure is erased. All that remains is geometry, pure, simple, elegant geometry described by a handful of numbers. In a sense, black holes are what objects become when you strip away all the details. When you remove all the contingencies, all the historical accidents, all the particular configurations, what remains is the essence, the irreducible core, and that core is astonishingly simple. 3 numbers, that's all you need. And from those 3 numbers, the entire exterior geometry follows uniquely, inevitably, beautifully. Black holes are the simplest objects in the universe, and that simplicity is the most profound lesson they teach us about the nature of space-time, information, and gravity.